Hi, we're the LineVision team, and we were working on encroachment detection. Before we begin, I'm Aditi. I'm joined by Amit, Daniel, Kate, and Olga. First, some background information. Power lines require monitoring to prevent encroachments or vegetation nearby from growing into their area of operation, for example, a tree branch. That's where LineVision comes in. Monitoring transmission lines is important because it allows us to maintain grid reliability by catching infringements early and reducing downtimes.
So right now, LineVision is using a technology called LiDAR to accomplish this. And LiDAR uses lasers in order to measure three-dimensional depth. And it works great. However, LiDAR is pretty expensive to set up. It requires a lot of complex hardware with moving parts, and it's a little limited in the exact kinds of information it can detect. Now, using cameras and computer vision can allow us to be much more granular with the exact kinds of data we can collect, all while being more cost-effective and power efficient. So therefore, our driving objective for this project was to recommend strategies for deploying computer vision onto edge devices in order to detect encroachment on transmission lines. And when I say edge devices, I'm specifically referring to running computer vision on hardware at the Powerline site itself, as opposed to in a central server on the cloud somewhere. And here's an exploded view of what that might look like. So on the device, we'd have a camera that can take photos of our Powerline scene. We now have two computer vision models that can then analyze that image. So the first is something called a segmentation model. And this can look at our image and determine exactly where the power lines and the vegetation are. With that information, we can then run a depth estimation model, which can look at our image and find the distances between all of the individual pixels. And so putting those two pieces of information together, we can determine if there's any point where the power lines and the vegetation are too close together where that would make an encroachment. Lastly, the device takes this information and uploads it up to a web dashboard where a utility company can monitor it and address any risks as necessary.
So how did we get to this full pipeline? The first thing that we did was create a data set for our model to train on, or basically learn how to identify different features. The first thing that we did was we acquired images from 3 different sources: Creative Commons images from LineVision, and also images that we captured ourselves. The next thing that we did was we annotated this data with polygons for the shapes that we wanted, and after that, we did some pre-processing on the entire data set to improve the contrast because power lines are thin and small. Finally, we did augmentations on segments of the data sets, so basically we transformed some of the images and parts of the images in order to mimic real-life weather conditions like wind, rain, with blurriness, noise, and rotations. The next thing that we did was we built our model, which basically takes in an image or one of our captures and outputs masks representing power lines, towers, and any vegetation. 2 important decisions that we made were, 1, to use an image segmentation model, which, as can be seen in the top right, creates masks for individual objects so that we can identify the explicit conductor that is being encroached upon. The second thing that we decided was to use a pre-trained model and tune our data set on that. So we used a model that was tuned on the common objects in context data set, and we built our training on top of that in order to get our individual object masks sort of specialized to our task. Finally, now that we have this model, we have to determine encroachment. We went about this via 2 methods. The first thing was to find pixel distances between objects, but this obviously has limited accuracy and high risk of false encroachment. For example, a camera or a branch right in front of the camera will be seen as a major encroachment alert when in reality that's just a depth perception issue. That brings us to our second method, which is to use a depth estimation model. This is significantly more accurate and compatible with our camera setup. However, we did encounter a challenge where we have to convert from relative depths, which you can see in the top right, to the actual depths. And this can be done by taking a few reference points from within the field, which is data that LineVision has access to.
Great. So now that we have our 2 models, let's talk a little bit about the process that it took to take those from our laptops onto some edge devices. And that was a 3-step process that we took. So the first is compilation. So this involves taking the models from the development formats on our laptops and transforming them into high-efficiency, compressed formats more suitable for small devices. Next is the execution phase, where we take those models and deploy them onto our hardware, running them with a standard set of test images. And while it's doing that, we can poke and prod it in all kinds of interesting ways to hopefully derive some useful insights. Out of these three, the most difficult was definitely compilation. It turns out that while our laptops are really good at testing different kinds of models really quickly, specialized AI accelerators, like the ones that we're using, are very particular about the exact kinds of models they can run. And at every step of the process, we found ourselves having to go back and tweak the model in order to make sure it was actually compatible. All that being said, we were eventually able to run some models and get some interesting data, which we have here. So we're primarily aiming to characterize three elements of our system. Number one, how long does the model take to run? This is plotted over on the left. The orange graph is in milliseconds. Number two is how well does our model perform? So this is the black line on the right. And we used a metric called mean average precision, or MAP, which is a number that can suitably wrap up many characteristics of the performance. Lastly, we want to measure how power efficient we are, and so this is the orange line on the right, plotted in watts. A couple of key takeaways here. If we look at the graph on the left, even at our highest image resolution that we tested, our execution time is still around a couple hundred milliseconds. And if we look at our setup, the cameras are mounted in a fixed position on the power line, and power lines and vegetation don't move very quickly, which means that our frequency requirements are quite low, on the order of once every few seconds or so. The second thing is, if we look at the graph on the right, we'll notice that performance actually scales up quite a bit as we go up in resolution, about 35% or so in our data. But the power cost that we pay for that is quite low in comparison, only about half a watt or so. So therefore, we move forward with recommending developing for higher resolutions whenever possible, because the power cost we pay is so minimal, and because we're not really approaching those low frequency requirements.
This brings us to our final recommendations based on what we tested and experimented with. The first is to create a custom data set with post-processing for changing conditions. The second is to train and fine-tune an instance segmentation model on said custom data set. The third is to use a depth estimation model in order to actually do the determining of what is being encroached. And the fourth is to consider hardware constraints early and develop for higher resolutions, as just mentioned.
And some of the potential avenues we see for exploring this problem face in the future include expanding our data set from the current 316 images in order to provide a more well-trained model. As I mentioned before, the scene isn't changing very much over time, so if we can incorporate in some data about where we expect power lines and vegetation to be, we can build a much more confident model that way. We can use some custom data or some synthetic data to much better tune our depth estimation. And lastly, we can fix the last few compilation blockers we have in order to be able to run tests out on the field. With that, I want to thank everybody who was involved in this project, particularly our advisor, Alessandra, as well as Steve Matsumoto, our subject matter expert, our liaisons, Dom, who's in the audience, as well as Mo, and everyone else at LineVision for helping bring this project to life. And you all for listening. Thank you very much.